Hello guys, hello, welcome to my YouTube video. It's been a while since I've made a YouTube video. I've been really busy with work, got a new job working outside, so I haven't had as much time to work. But I've been doing stuff on the side here, and I wanted to make a video on some stuff I've been doing. So recently I've been working on GPU optimizations. Specifically, I've been working on a NVIDIA library called nvMolKit. And I'm not sure if some of you have heard of RDKit, but it's a library to do a bunch of chemistry related tasks, bioinformatics, cheminformatics type tasks. And it's really crucial in a lot of these, to do these tasks, but sometimes it can be really slow, right? So nvMolKit is just a high performance variation of RDKit that runs on the GPU. And the reason I even found this is because I was running into throughput issues with my RL conformer generation environment, right? I couldn't get as many experiments as I wanted because my GPU was just too slow. I was getting bottlenecked by speed. So I found this, I took a look at it. I really enjoy GPU programming currently. And I decided what better way to work on it, look more into it and work on this. I've been putting in some work on this, conversing with I believe it's Scal 444 is the name of the maintainer that's really been giving me tips and stuff to improve, and I really appreciate it. Here he is. I'm not sure if he has. Oh, oops. But yeah, he's giving me tips. I've been working on it. It's been really fun. And yeah, I've got several this is my second one. Yeah, this is probably my second PR, I believe. My first. I believe it's my second one, but regardless. It was the whole point of this was to optimize one of their clustering algorithm variants called fuse Butina clustering. And originally it was running on Python and Triton, but I ported it to CUDA and I had to make it a bit faster. I got it up to, on average, I believe it was 4 times faster. Yeah, it started, my first initial results were a bit slower, but then I was able to get it to about, on average, 4 times faster. So I'm going to get into a bit of some of the optimizations that was done. So yes, let's hop into some of the optimizations that were done, right? So number one, first optimization that was done was converting, the process of converting the fingerprints matrix to a distance and then a hit matrix, right? So we'd have each of these molecules would have a fingerprint, and then would be which is their representative set, or why am I keep saying representative? Would just be their set of their features, which would be comparing against the other molecules, right? And then I'll just take higher level. So if we see here, we'll be doing for this molecule, we'll be doing n comparisons here. Then for this row, n comparisons, n here and n. So we'll be doing n squared comparisons, which is the amount of values that will be in this table. And notice that we'll be have a block, right? So the way I originally wrote the kernel was that I'll have a block that will, for each molecule, will compare its pairwise fingerprints to all other ones. And for molecule 2, I have a block compared to all other ones, and then here it'd be the same to all other ones, and then 4 would be to all the other ones. But notice that will lead to n squared work, of course, but also n squared shared memory loads, right? If I delete all of this, the amount for each molecule here, if I load in this molecule, when in this block, I have to load from global memory into shared memory, because remember, this matrix is being stored in global memory. It's way too big. Actually, in the fused approach, it's not even being stored in or inside the block where the kernel memory. We're computing this on the would be running, right? Or is it the block kernel will be running? It'll be the block, but the block that'll be running the kernel. Yeah, that's proper phrasing. So here in shared memory, when we launch the kernel, yeah, we'd have to load each of these. So we'd have N in black, I'll have work done, but in orange, I'll have shared memory loads. So I still have to do N squared shared memory loads, right? For each of these molecules, I have to load in this fingerprint, this one, this one, this one, this one, this one, this one, this one. Because remember how I do these in the blocks, right? So I'm gonna have N squared memory loads. The first optimization is to reduce this, not by asymptotically, but in practically by some constant factor. So the way to do this, you have an approach called tiling. So yeah, in each of these blocks, note how I have to load in N memory, right? What you can see is that there's a lot of redundant memory loads being done, right? Here for molecule 1, I load molecule 2, I load molecule 3, molecule 4, and of course I load it in itself. But notice that when I do molecule 2, even though I already had some point in time in this other kernel block, I had molecule 2 and 1 in memory, I still reload molecule 1 and molecule 2, right? 2, 2, 2, 3, and 4, 4. And notice that the molecule 3, in some point in time, I had 1 and 3 loaded, and not just that, but I had 2 and 3 loaded once, and I had 2 and 3 loaded twice. So you can see, if I already had these loaded twice, 2, 3 loaded twice before, and 1, 3 loaded once before, why am I loading this again? I load 1, 3, and then I load 2, 3 again. So you can see how we have all those repeated shared memory loads being done. So a way to get over this is an approach called tiling, where instead of repeatedly redoing these memory loads, we could load all these molecules once and then compute all the pairwise fingerprints, compute all of them pairwise, so that we avoid having to reload them in the future, right? So the way this would be done is we'd have these would be broken down into tiles. Here they're size 4, but the way I implemented was size 64, 64 by 64 in the actual implementation. And then for each of these tiles, we're gonna be loading in, example here, I loaded molecule 1, then I loaded molecule 2. So at most, I'll do 4 memory loads, right? 1, 2, 3, 4. Notice how I have to load in for this tile. I have to load molecule 1, molecule 2, molecule 3, and molecule 4. So I load in 4 molecules, right? But I compute all the pairwise fingerprints between them here. So I don't have to touch molecule 3 and molecule 2 again here, right? So yeah, I run this tiled approach here. And then, yeah, I split these up into tiles, and then I compute all the pairwise between these tiles. So, I want in the other kernels, this will greatly reduce the amount of work, right? You might not be able to tell right now, but let's just run through some math to show you. So originally I had n squared comparisons, and of course the total amount of work doesn't change. I have n squared comparisons here, but now this new tiling approach, I'll have n squared, which was the original n squared memory loads, right? Or let's do by blocks. So these are the n squared values, and each block is size 2 by 2, so 2 squared. This will give me the amount of blocks I have, and so this is the amount of blocks I have, given that they're 2 by 2. Now if I want to know the amount of loads I have per block, I have Potentially, if it's 2 by 2, I have 2, 4. So I have 2 times 2 loads being done per block. So then if I multiply blocks by loads per block, what do I get? I get n squared divided by 2 squared times 2 times 2. And if I divide this 2 by this 2, oh, what the heck? Oh, this is oops, this has been one of the worst examples to show this. It really doesn't cancel out nicely here. 2 by 2 blocks on a 4 by... Okay, this is a really bad example. Frick. Because this 2 is irrespective of here. Here they'll fully cancel out, but it's not supposed to be like that. If this was, for example, a 3 by 3 matrix. Let me erase this. Let's say instead of using blocks of size 2, I was using blocks of size 3. For this example, we can't be shown nicely. But I don't want to have to redraw all of this. Let's suppose we're using blocks of size 3. Then this is the amount of blocks we'd have. So we'd have n squared elements divided by 3 squared, which is, it'll be the size of a block. So we'd have this many blocks. And then work per block, once again, would be 3 times 2. So we do 3 loads for the top and 3 loads for the side. Now in total, the amount of work that will be done here, or memory loads, would be n squared divided by 3 squared times 3 times 2, right? If I divide this 3, we're left with n squared times 2 over 3, which would be equal to essentially 2/3 of the amount of memory loads, right? Originally we had n squared memory loads to the original approach, but we have 2 over 3 loads, right? So we reduced the work by quite a bit. We're only doing 2/3 of the initial memory loads we're doing. Now the greater these block sizes, the greater the factor that reduced the work by, right? Which is why I was using these 64 size blocks. Up to some constraint, but yes, I'll show you what happens if we use blocks of size 64. This was a bad example to show this. I didn't realize it now, because it really makes sense of a lot of data. But imagine we have thousands and thousands of molecules, right? And then we're using blocks of size 64. Let me just amend this here to show you how much the work would be simplified by. We'd be doing, so n squared elements, the blocks would be 64 by 64 squared, so we'd have this many blocks, and then work per block would be 64 times 2, right? We would load the top 64 elements and the side, or the horizontal 64 and the vertical 64, so it would be 2 times 64 memory loads. And then if we compare the load, we multiply blocks by loads per block to get total loads. We have n squared over 64 squared times 2 times 64. We'll divide the 64, we end up with 2 over 64 n squared, which would be equal to 1 over 32 n squared. So look at this. We're only doing 1/32 of the work we're already done with blocks of size 64. So you see how this can greatly reduce the amount of shared memory loads we're doing, right? By using tiling. We went from n squared to 1 over 32 n squared by using 64 by 64 blocks, which is what I was doing. So yeah, I reduced that was the first optimization to reduce the work by quite a bit, right? Only do 1/32 memory loads, which really sped up the amount of work I was doing. And the second optimization out of the 3 was realizing taking advantage of the symmetry of the matrix, right? Suppose we have some matrix right here, right? We'll do 3 by 3 again. Or what the heck am I doing? That's not 3 by 3. Just do 3 by 3 for now. 1, 2, 3. I'm gonna go 1, 2, 3, 1, 2, and 3 here. So yeah. The thing that we didn't realize is, for example, number one, similarity between these diagonal elements are always 1. Because this would be similarity between the molecule 3 and itself, which is always 1. But let's say we just put in random values here. The key is that similarity between 1 and 2 is equal to similarity between, or 2 and 1 is equal to similarity between 1 and 2, right? These are the same. The similarity between 1 and 3, let's name it 0.6, is equal to the similarity between 3 and 1, right? So 3 and 1 should match 1 and 3. And the similarity between 3 and 2 should match 2 and 3, right? So you see how this matrix is symmetric? We could greatly abuse this, right? What we can do is that instead of running O of n squared computations like we're already doing here, right? We only need to do the upper triangular, right? Anything or upper or lower triangular, right? I chose to do upper triangular, but if you like, you can do lower triangular as well. It doesn't matter. But anything below the diagonal here, you could just ignore, because you know, if you have this value, you automatically know what this value would be, for example, because of the symmetry property, right? So by doing this, we reduce the amount of computations from n squared to, we only need to compare the pairwise elements, right? So it would be something like, if we only had 3 elements, we'd have to do, let's say we had 3, 2, 1. We compare 3 to 2, 2 to 1. Compare 2 to 1. If we had something like 4, 3, 2, 1, we do 1, 2, 3, 1, 2, and then 2 to 1, and then 1 to 1. So it would look like something like this: 3 plus 2 plus 1 here, and here it just looked like 2 plus 1. So of course, if you noticed, like, this looks like an arithmetic progression, right? There's a formula for this in discrete math, found by, what was his name, Ghost, that little genius mathematician. He found this out when he was a kid, but anyways, the formula for this progression is n times n plus 1 divided by 2. Actually, there's a video on my channel on this too, the recursion video. In this video, if you want more, you're a bit confused on this idea of the progression, you can look at my recursion video from 4 years ago. I actually remember talking about this, showing geometrically how this formula makes sense. But anyways, that's not important for now. Only thing important is that you reduce the work from n squared. Let me erase this. Back. From n squared to n times n plus 1 over 2. Just n squared plus n divided by 2 divided by 2, right? So that's the second optimization that was done by only comparing the pairwise stuff. And actually here it would actually be n minus 1. Since we have to include, we don't need to compare them to itself. So this would be, we delete this. This would be from n squared to n times n minus 1. Still, you could look at my video if you're confused about this, which would give, it's just the basic arithmetic progression formula. This is the amount of work that will be being done, right? Which of course is faster than O of n squared. So that's another optimization that was done. Reduce computations from n squared to n squared minus n over 2. So the first optimization was targeted at shared memory bandwidth. The second one was targeted at the total amount of work we had to do. And now the third optimization, actually let me just write these out. So first optimization was shared memory. Bandwidth. Second was total computation. And the third one is atomic pressure, which is what I explained here. Reduce the amount of atomics we're doing. So actually this was the maintainer in the library is actually the one who gave me this tip to reduce this. So what I was doing is that, okay, once I've obtained all these previous steps, which is to based on the fingerprints to determine which of these molecules are neighbors of each other. So after I've done all this work, I need to make that vector I was talking about, or the vector of given each molecule, how many neighbors each one has. I need to look over, I need to sum over whether or not this molecule 1, for example, was a neighbor with molecule 2, whether it was a neighbor of molecule 3, etc., right? And the key idea is that because I'm using this global vector, and I'm using individual threads for each of these, I need to use atomics to make sure, well, this was my initial thought process, but I thought I had to use atomics to make sure that I don't mess up adding to these neighbor counts, right? But the thing that could be done is that, sure, I still have to use atomics, but I could do warp level reductions or block level reductions to reduce the amount of atomics I had to do, right? So for example, suppose I have 100 elements, right? Or let's say 100 threads, and each of these threads need to access this one memory position. Just name some random memory position. 0, F, F8 or something. And each of these need to access this memory position. Right. Or just one arrow here. X 100. You'd see, and they're doing it in parallel, right? You'd want one trivial way, which is the original way I was doing it, was that I have each thread lock up this position, right? So I'll do an atomic addition over here. So I'd have each thread perform an atomic operation here. So it would lock up this memory, then it would write, then it would release it on a lower level, right? So this would be done 100 times. Now, that's a lot of atomics for 100 here, right? Compared to what it could be. One smarter way to do this, instead of each thread accessing atomically this memory location, I could split this up into, say, we know warps are size 32, right? So I could split this up into size 32 blocks. So I'd have 1, 2, 3, and then I have a final block, but this one would only have how many? 4 extra threads left over, because this is 96, and this would be 40 create 100. So I could split up this 100 into blocks like this. Right? And then if I'm able to perform additions within this blocks efficiently, then I only need to do 4 memory accesses, right? This accesses this once, twice, 3, 4. So I went from 100 atomics to only 4 atomics being needed here. Just on if I'm able to somehow perform these block or warp level reductions, right? So instead of each thread right in here, I have a leader of each warp which is these threads, group of threads of size 32. I have the leader right into this shared memory, right? Or shared right into this global memory. So the way I do this is I had some warp level atomics. I used a ballot, right? So let me load this up here. It'd be here. I'd have the warp level ballot atomic, right? So essentially what this is doing is that for each thread in the group of size 32, which is here, what it's doing is that it's writing into some, it'll be memory location size 32, it'll be an integer here, and it's accessing the bit positions and it's setting it to 0 or 1 based on whether or not the molecule is a neighbor of another molecule, right? So we run those warp level, and then once we do that, notice that now we could just pop count to count how many of these are set to 1. So we have each of these perform the ballot atomics, and then within that return value we could count how many bits are set to 1, and that tells us the neighbor count, right, for the corresponding molecule. So if we, instead of doing the 100 atomics here, we could perform a warp level reduction, do the ballot, pop count to count how many, the pop count instruction, which, where is it being done here? I think this is further downstream. Nah, the pop count is for the higher level. This should be done at a deeper level. The ballot. Yes. Okay, here we go. Frag, I wasn't seeing that properly, so we sync them up. And then okay, here we go. This is correct now. This is the second pop count I was looking for. So in this pop count, what we're doing here now is that we're counting how many of those bits were set to 1. So note that this is really fast operation, and just bit operations, which is done really fast on CPU or GPU. And then now, after we've done that, we just do 1 atomic, right? So this is the leader of the thread. We do the 1 pop count. So instead of doing these 100 atomics, we do 1 ballot, which is the warp level reduction. 1 warp reduction into 1 pop count into 1 atomic. Now this is okay using 3 operations instead of 1, right? Because these atomics are way more expensive, right? We want to always make sure to fully use the parallel resources on the GPU. So even though we went from doing 1 operation 100 times to doing these 3 operations, right? The key idea is we're only doing these 3 operations based on how far we divided this block, right? So, and we're doing way less atomics, which is what's really expensive. So for example, if we had 100 and we split it up into warps of size 32, we'd only have 4 blocks here. So we'd be doing 4 atomic adds instead of 100 versus 4. So this was the last optimization that was done, which I didn't realize. I'm grateful that the maintainer showed me that we could do something like this. So yeah, we're able to further reduce the amount of work, and this will reduce the amount of work by, or the amount of atomics by the size of blocks, right? So here, if we're using 32 size blocks, we reduce it by a factor of 32, which is around 4. 100 divided by 32 is around 4, right? So here we're doing 1/2 atomics. That was the 3rd optimization that was done. So yeah, Codex wasn't able to get a lot of these optimizations offhand. I had to, for example, this last one on atomic pressure, this idea was given to me by the maintainer. Same with this one, I looked at some other examples. Total computation, Codex, yeah, Codex fully came up with that one, but it was still quite a bit of work to do all these different optimizations. But yeah, I just wanted to make a short video on some of the stuff I was doing, some of the optimizations that were being done. And yeah, I think that's it. I know it's a bit of a longer video. I tried to make it as short as I could. I was trying to speak faster, but it might have come off as rambling. But thank you guys for watching. I really appreciate it. And yeah, see you guys later. Bye.